right, looks like this should be working. And yeah, I guess if anybody's in the Slack channel, maybe you can let me know if you can see me and if everything seems to be working normally. Looks like, at least from my end, everything should be okay. But it'd be good to see in chat or on Slack that you can actually see and hear me before we start into looking at the stuff for the Geo-Python course for this week. So I'll just wait a second, and then we can get to talking about where we left off last week about functions, maybe as a starting point. Let's see. I'm not seeing any activity here. Oh, maybe we got something. Yeah, okay. At least there's one response here that everything looks good. So, okay, well, that's good news. And then, yeah, I guess the thing we're going to talk a little bit about today, maybe a starting point, would be to talk about functions, because last time when we had our discussion, it was mostly just talking about for loops and conditional statements, and we didn't really get into functions, and that was one of the questions that was asked. And I thought we could also maybe talk a little bit about Numpy if we have some time. So let's maybe start, and I'll just remind you that if you have questions, there is a thread in the Slack for this week's live stream lesson thing. So you can put some questions there if there's certain things you'd like me to discuss. But otherwise, we'll start here just by talking about functions a little bit. And just as a kind of opening point, I think the first thing to think about when we talk about functions is why would we even bother writing a function? It's not always something that is obvious to you in terms of how it works. And there are some cases where you might think it's more confusing or more work to write a function than it would be just to write the code that you're using out by itself. But there are very good reasons for using functions. And we can start by maybe just talking briefly about those reasons. So I guess I'm going to assume that you guys have looked through at least a bit of this lesson material about the kind of general anatomy of a function, sort of what are the different components to creating it. I'll go through a couple examples of defining functions as part of the lesson here. But yeah, the main purpose is basically just to take any piece of code that you're going to be reusing regularly and convert it into something that is easy and safe to reuse. So if you can make a function that will do some kind of calculation or something you want to do in your code, and it's very easy just to call that function with some input data, then there's good reason to do that. The biggest reason for doing it is just every time you copy and paste some part of your code, there's a chance that you'll make a mistake somewhere. Whereas if you define a function, you test it and you know that it works, then you can just keep reusing that function as much as you like. So that's the kind of idea behind it. Is basically it is a self-contained little piece of code that once you've tested it and you've tested all the various cases you could think of to use it, then you've got this nice thing that can easily be reused and allow you to avoid the possible problems that might come with, let's say you had typed out something to calculate, the time in seconds or something like that from some time in thousands of years. You had written some code that did that, but every time you sort of copy and paste the code. Maybe you make some changes, or maybe you, even worse, you made a code that would produce some kind of plot or something, and you change the plot format. If you do this with a function, you just change the function, and then all of the subsequent plots would change. If you do this in a code where you just have in some lines a description of calculating something or making a plot, every place you have that code, you then need to go and edit that same piece of code in order to change something like updating the axes of the plot or something like that. So enough with the kind of talking. We can get to some examples here. And I thought maybe what we could do is we could define a few functions. The first one could be something that would convert time in years to time in seconds. This is a very common thing to have to do, particularly for using various equations in geophysics, for example, because oftentimes you're wanting to work in units of seconds for the time instead of years or millions of years, which are more common for geological data. So let's start with that. And we're going to create a function. So the first thing we need to do is have this define, this def statement, where we say we're going to create some new function. And we'll call our function years to sec. And it's going to take one value as a parameter, time years. And so we've created this function, or we will create it, called years to sec. It's perfectly fine to have a number inside the name of the function. And then we're saying it's going to have one value that you would pass into it, and the expectation is that that value is a time in years. Now, we could go through a painful process of trying to make sure that the code actually checks to see that the time is in years, but we're just going to assume in this case that the user has supplied a number and that that number is a time in years. So with our function, all we really need to do is one calculation, and that is that we want to say time seconds is equal to whatever it takes to convert time in years to time in seconds. So in this case, it's going to be time in years, and then we need to multiply by the number of days in a year, so 365.25, include our leap year. So we've got from years to days, and now we need to go number of hours in a day, so there's 24 hours in a day, and then 60 seconds in an hour, or 60 hours, 60 minutes in an hour, and 60 seconds in 1 minute. So that should take a time in years and multiply by these different conversion factors to give us a time in seconds. And then all we want to do at that stage is just return time seconds. So we have all the pieces then for creating this function. We have its define statement, we have the name of the function, we have the parameter it's going to take, in this case time in years, and then we do some calculation and we return a value. So we can do that. And what we can see here now is that we could test it out. So I don't know that anybody really knows right offhand how many seconds are in a year, but we can just check and see that if we do years to sec, call our function with 1 year, do we get back some kind of reasonable number? So this says there's about 31,557,600 seconds in a year. So 3.15 times 10 to the 7 is about right. That is the number of seconds that we have in 1 calendar year. And so, we would probably want to cross-check this with some resource. There's plenty of places where you could go online, like you could go to even Google or Wolfram Alpha. It's kind of online, gosh, I don't even know what you would call it, some kind of computational knowledge database. But you could say, year in seconds on the Wolfram Alpha page, and it will go through its calculations and come back saying there's 3.154 seconds, or 3.154 times 10 to the 7 seconds. That's pretty close to the value that we're getting here. We get a little bit different value, perhaps because we've used 365.25 instead of just 365. But there you have it. So it looks like our years to sec function is working as we would expect. Now, what we could say then is basically any time that we want to convert time from years to seconds, we now have an easy way to do that. So that, if you had some variable you wanted, like 10 years in seconds, or 10 years in sec, you could then just say that that's years to sec of 10. And so then, if we wanted to, we could say print. And since we talked about this last time, we'll use the fancy formatting. There are, let's go with this 1 decimal point of floating precision. We don't need it really, but we'll just do this 0.1f. So there are that many seconds in 10 years. And then we're going to add our dot format string, or dot format function after this text in quotation marks. And the thing that we want to format in this case is 10 years in sec. And so if we print this, we then get there our 315,576,000 seconds in 10 years. So some big number. Just for the sake of demonstration, I'm just going to copy this here and show you that if you wanted to instead have this as a scientific notation, you could do that and maybe say, okay, instead of 1 decimal place, we want to have something more like 6, because it's going to only show us the 1 value in front of the decimal here. So if you prefer to print things out this way, you could say there are 3.15576 times 10 to the 8 seconds in 10 years. That's not so much related to functions, but just in case you were curious about how to do scientific notation versus just floating point numbers, there's a nice example. Now, if someone else was using your code and they saw this years to sec function, there are some things in built into Python to allow you to get some documentation about things like functions. So there's a thing called doc years to sec, and doc is not defined. Maybe it's help. And now it's complaining about that. Does this need to be in parentheses? Okay, sorry. So it's called help. I thought it was doc, but so help, if you use that and then you give some name of some kind of function or something like that, normally what it would do is pull up a little bit of documentation that helps you understand what that function does. So here it says help on function years to sec in module main. So this is just telling you where it came from. We've defined it within the main program here, not in some other script or something. So it just comes back saying it's in the main module. And then it says years to sec, time in years. So all it really does is show us this little piece of the function there, which is its name and the parameter it accepts. That can be enough information in some cases, like this might tell someone a little bit about what this function is supposed to do. But what's better is to add some little string of text here that says converts time in years to seconds. And so this is called a doc string. It's just a short little piece of text. It's immediately under the definition of the function, indented like the rest of the stuff inside the function. And it's within, all the text here should be within triple quotation marks. Whether you use single quotes or double quotes doesn't really matter, but you have to have 3 on either side here. And so you can add basically as much documentation as you want here, but usually you should at least have one sentence that says, what does this function do? And then if we run this cell, we'll just update the definition of the function in memory. And now when I do help years to sec, what I see is that years to sec converts time in years to seconds. I guess this actually probably doesn't need to be indented. No, it does need to be indented. I was wondering because of the indentation of the text here if I could get away without indenting, but I guess not. So anyway, obviously that's a bit more helpful for someone who's trying to figure out what this function does. And it's not actually a bad idea, even in writing your own code, to include little doc strings like this that just tell you what the functions do, because sometimes, as much as you try to name functions useful things and make it obvious what it does from the name alone, if you've got a lot of things going on in your code, it can be a little bit confusing, and just being able to bail out to the help and say, what does this thing do, is pretty handy. So I would say that that's a worthwhile time investment to just take 30 seconds, think about some simple statement of what your function does, and add the text in there as a little doc string on one line or more lines if you feel like you need it. So that's a basic definition of a function, and I guess probably that part is fairly clear. There were a couple questions earlier in Slack about this stuff, so I'll just mention that generally speaking, if you're working in a Jupyter notebook, normally what you would do is define most of the functions at the start of the notebook. If you're writing your code in a Python script, you would also basically do the same thing. That usually you put more or less like right after you would import any of the libraries or modules you're going to use, you would then define the functions at the top of the code. If I was, for instance, here to go and let me see if I restart my kernel, that will delete all the everything that's in memory right now. So if I just restart this kernel, now we don't know about the years to sec function because it hasn't been defined yet. And if I try to use that, of course, then I get this name error saying years to sec is not defined. So if you expect someone to use the function, put it up at the top so that if they're running your Jupyter notebook, they'll run those cells first, and then when it comes time to use it, then the function works. Okay, so we got years to sec. We can add another function here because converting years to seconds is perhaps fairly common, but it's also common to do conversions like millions of years to seconds. And we're going to do this in 2 stages. So first, we're going to define something called my to, let's say, I guess my is not a very good name here. Let's just call it million years to years. Okay, it's not the best function name, but that'll work for our purposes. And this should take a time in, we'll just call it MA for millions of years. And so with this function, we'll do the same thing we did before. This is going to convert time in MA to years. All right, and we'll assume our users know what this is. We could also just say millions of years to years. It's kind of as you please. If you want to be more explicit here, it's usually not a bad thing. And then we can now say our time in years is equal to our time MA, which was what's come in. And if we want to convert time in millions of years to years, this is almost not worth making a function to do it. But it's 1 times 10 to the 6 that we're going to multiply to go from MA to years. So that's an easy conversion, and then we're just going to return, in this case, time underscore years. So that looks very similar to what we did with years to seconds. And we can run that cell, and then if we went down here someplace and just said, well, how about million years to years, I can hit tab, or the tabulator key to auto-complete that function name, because there's nothing else that will start with million. And if we said 10 million years, sure enough, we get 10 million back when we convert million years to years. Now, okay, what's the point of doing that? Well, the point is that what we want perhaps to have ultimately is a function that will convert from million years to seconds. And that's what we're going to do now, is we'll define a third function. In this case, we're going to call this, I guess I'll call it MA to sec, just to give it a little bit different name than this million years to years. And in this situation, what we expect, again, is to have a time in millions of years, so time MA. So we have our MA to sec. This function will give a doc string as well that will convert. I guess this should say converts up here. So converts time in millions of years to seconds. All right. And what we're going to do in this case is now we're going to take advantage of the fact that we've already defined functions to do all of this work. And that is that we could say here, first, let's convert time MA to years. And so we can say time years equals, and we'll just use our example from what we had defined here. And that is that we'll use our millions years to years function with time MA. That's what comes into the function here. So whatever that value is will be used inside here. And then also we can look at converting then from time in years to time in seconds. And so then we can say time underscore seconds equals, and I'm just going to copy paste the name years to sec, because we're using basically the same kind of naming here. So then we're going to call a years to sec function from within here, and then we're going to return time in seconds. So it's a lot like what we did already up here, and you know, this is sort of a toy example in the sense that you could certainly come up with more complicated functions that you might define and then link together, but this should work for the purposes of what we want to do. So by running this cell, we're now going to define all these functions. We should have MA to sec. Since it has a weird name, we could go down here and check the help on MA to sec, and we see that it's converts millions of years to seconds. So we had done million years to years earlier for 10 million years. And if we do MA to sec for 10 million years and run that, we now get a pretty big number. It's, well, I don't want to bother trying to count the decimal places, but it's going to be something like 3.15 times 10 to the 11, or actually maybe 10 to the 14. So it's a pretty big number. If we wanted to say time seconds equals that, we could then have a print statement and use the scientific notation to figure out how many decimal places we actually have. So we could say here, there are, and we'll again do the nice formatting. We'll do 0.6e. So scientific notation, 6 decimal places. There are this many seconds in 10 million years. And so all we're going to do is we'll have our print statement, and what we want to print out is our time underscore seconds, because that's what we've calculated right here. We did MA to sec with 10 million years, store that as time seconds, And then we're going to print our print statement with time seconds going in here in that place. And as expected, there are 3.15 blah, blah, blah times 10 to the 14 seconds in 10 million years. So, this is, again, maybe not the most demanding example to think through, but the point here is that converting time from millions of years to seconds is something you might have to do pretty often. And you might think like, okay, well, every time I need to do it, I'm just going to say like 10 times 1 times 10 to the 6 times 365.25 times 24 times 60 times 60. And of course, you're going to get some big number out of that, and probably you're all looking at this saying, well, you put 265, not 365. But that's the point. And that is that you can easily make these kind of mistakes typing something in like this, put in, the wrong value here for when you convert from years to millions of years or whatever, 34 instead of 24, whatever. It's easy to hide because if you don't know, we're using a number of 10 million years, but if you had something like, 5.8, I don't know how many seconds are in 5.8 million years. And if I have a function that I've tested and I know the output, it's much safer for me to use that function to convert 5.8 million years to seconds than it is to just multiply by 1 times 10 to the 6, 365.25, 24, and then 60 times 60. So that's the kind of benefit here, because I couldn't tell you from looking at this big number. I know that's a lot of seconds. That could be how many there are in 5.8 million years, but in fact I would be wrong and off by a substantial amount. So are there any questions maybe at this point about how the functions work and their definitions? There was maybe one thing I was going to say just about, I think this is actually something that came up in an earlier lesson talking about functions and the kind of namespace for functions that, when you pass something in here, time ma, what's going to be used in the function is the value of time ma that's passed into the function, even if there is a time ma that's been defined outside of the function. So you have to be a little bit careful, and sometimes it's confusing that if you have variable names that are the same as the value you pass to your function, you might get confused about how that all works. But essentially, whatever happens in the function is sort of disposable in a sense. So it's going to operate with whatever information is passed in. If there are variables in the main namespace, it can access those. But basically, you should assume that if you have a function, you should be passing in everything it needs to do whatever the calculation is. So if you wanted to, for instance, figure out how many seconds are in a given month, then what you would need to do is pass in not only the way to convert from days to seconds, but also which month it is and the number of days in that month, so that you can figure out then, okay, well, if it's February, it's going to have fewer seconds in that month than, well, any of the others. So, to do that calculation, you need two pieces of information, not just the conversion. So, it'll depend a little bit on the situation that you're facing. So that's kind of what I had in mind for functions. And if I don't see any questions in Slack, then maybe what I will do is talk a little bit about Numpy, because there were some questions about like Numpy versus pandas. Why do you want to use one or the other, and what's the benefits and things of that nature. So I can talk a little bit about that stuff just briefly, and then maybe show a couple things in Numpy that are useful. This idea of masking data is always something that's kind of challenging, so I thought maybe I could make some arrays full of like junk numbers in Numpy and then play around with those a little bit. So let's add a markdown cell here. I was thinking about it just now that maybe would it be useful for me to put these notebooks, like even though they're full of kind of like dumb examples, would it be useful to share these? I can put these in Slack if that's helpful. I hadn't really thought about it initially, like of course not thinking ahead that I could kind of put some documentation in these things as we work through them, but I can put this in Slack or somehow make it available. Maybe I can somehow, well, I'll figure out something. But yeah, we're going to talk about NumPy stuff and pandas in general. And the first thing is just to sort of distinguish between the two. So both of NumPy and pandas are meant to make dealing with data in Python a bit easier. NumPy is kind of built around the idea of doing a bit more numerical stuff, so a little bit more on the computational calculations and solving equations and processing big data sets. It's the kind of focus of things like NumPy. Its name alone would clearly indicate that it has something to do with numbers. And sure enough, if you look at the NumPy website, you can go there and easily see that there's a basic description here in somewhat computational terminology about what NumPy does. But essentially it's got functions and functionality for processing scientific data in typically it's big data sets, large amounts of numbers, and it has its own structures. The main thing being this what they call an n-dimensional array object. It's kind of like a Python list, but it only holds one type of data, and because it only holds one type of data, it's a bit more efficient when you start dealing with large numbers of values in an array than something like a list in Python, because a list in Python could contain anything, basically. Could be variables, could be other lists, could be text strings, and because of that, it's just a bit more bloated and not quite as efficient when it starts being filled up with large numbers of values. Now, pandas, on the other hand, is a data analysis library, as the name says here. I sort of see it personally as something that's built more around the idea of loading in data files and interacting with data that's somewhat like spreadsheet format data, so like comma-separated value files where you have a bunch of different columns, and each column contains different values in it. And so I think by comparison to NumPy is a little bit more on the kind of computational programming side of things and more in that approach, whereas pandas I see a little bit more, it's certainly written in Python and it's a Python library, but I see it a bit more as something that's working closer to like dealing with spreadsheets. And you see that even in the format of the data, this data frame in pandas. I don't know if there's an example on the pandas web page that kind of shows you what the data frame looks like, but you can see it on the Geo-Python page if you go, for instance, to the pandas lesson and start looking through exploring data using pandas. There's some places where there are print statements like here, printing out a data frame. And what you see is essentially data in columns. In this case, there's a bit of a need to skip reading over the header, and then you see nice looking data where you've got this data frame, you've got names of the different values at the headings of the columns, and underneath that, then you've got the values themselves with some kind of index over on the left. And this is typical Python indexing on the left side here, where it looks like there's 30 days worth of data, and so the index starts at 0 and ends at 29. Now, one of the cool things in pandas is that you can make the index actually not just be some Python integer number, but you can make it be a date time type of index, which is pretty cool because then it makes it easier to slice out data by date. But I'm not going to get into that part right now, just kind of showing you that the kind of pandas approach looks much more like you're dealing with kind of spreadsheet types of data. So in terms of like what's more useful to you as a new Python learner, I would say that my general recommendation would be that people learn pandas, because I think oftentimes most students are dealing with tables of data or Excel files in many cases, and as those files start to get big, it becomes cumbersome to deal with them in Excel, and that's someplace where learning a little bit of pandas could be quite helpful. And you can also take things like some of the climate data that we're using occasionally in the course, where you might have huge amounts of observations, tens of thousands, hundreds of thousands of observations, that are far too big to go into something like Excel, but could easily be dealt with in pandas. So my general recommendation actually is that I think, this past year in the Geo-Python course, we taught both pandas and Numpy. We split the group. When we taught the course here in Helsinki, we split into a Numpy group and a pandas group. I think this year we're going to move back to just teaching pandas to everyone, because I think it's more useful as a whole for everyone. And then we'll learn a few things in Numpy that we need, because that's it's necessary for some of the other Python-based courses that we have that continue here. So it also happens that pandas extensively uses Numpy as a kind of like under the hood sort of computing part of what pandas is doing. A lot of it is actually done in Numpy, but you just never see that. It's like the functions that you're calling, the things that your methods you're using in pandas are using Numpy, but you just don't ever know about that. So in fact, I think the pandas data frame is in many ways kind of built upon the Numpy n-dimensional array, although probably I could sit here and read this pandas webpage and quickly show myself that I'm wrong. But the bottom line is it's under the hood somewhere. So what I want to talk about a little bit with Numpy is, even though I've just told you, that I suggest using pandas in general, I wanted to answer a couple questions about stuff in Numpy, because I know a few people have done some of the lesson 5 and 6 using Numpy, and there are some things that can kind of be done in both pandas and Numpy that are similar, and in some cases things are a little bit different. But what I thought we could maybe do is start out with just making some list of values that's full of just junk numbers, and then using these masks to select only some numbers from some array of values. First thing we have to do is import Numpy, and we'll just import Numpy as NP. So that'll make the Numpy library available to us. The NP just is a shorthand way of writing Numpy. So you kind of, every time you want to use a function out of Numpy, you'll do np dot something instead of typing numpy dot whatever. And we can use a few different functions. There is one here called np.random.rand, and if you give it some number, np.random will give you then back 5 random numbers between 0 and 1. So here are our 5 numbers. They go into this thing. You can see here it's an array. So this is one of these Numpy arrays. And what we're going to do here is we could say np.rand minus 0.5. And what that should do is then give us numbers that are basically from minus 0.5 to positive 0.5. So it means we have positive and negative numbers. And then that's something we can play around with in our example that I'll show you about using these masks. So what we could say then is, let's make a variable now that we'll just call random values, and we'll make it be np.random.rand. And since we're using Numpy, let's give it some reasonably big number. Let's give it 100,000 random values. Like before, we're going to subtract from each one of those values 0.5, so we should get some distribution where we have numbers from minus 0.5 to positive 0.5. So that's our random values. You can see it's pretty quick that we have that. And if we check out what's in there. You can do that just by typing its name and hitting enter. Of course, with the NumPy array, it's not going to show us all 100,000 values. It shows the first 3 and the last 3. And sure enough, they look about right. So we got numbers from minus 0.43 to plus 0.46 in just a small sample. So it looks like we got the random numbers that we expect. Now, there's a few things we can do here. We can do some slicing of this array. So looking at just select values out of the array. And then we can also do some of this masking of values in the array. And let's start with just slicing because it's a kind of common thing you need to do. And so like, let's say you only want to see the first 10 values out of our random, I'm good at spelling, random values. And to do this, we're going to take the square brackets after the name of the variable because it's an array, it's just like a Python list, and say we only want the first 10 and nothing. Did I do that the right way? I think what I want is the other way around here, to go from 0 to index 10. And if I run this, then I get 10 numbers back, and these are the first 10 values from my random values. So if I typed in 0:10, I'd get the same output. That's just saying take the value from index 0 up to, but not including, index 10. So if you count the numbers up here, there's 0, or their sort of index values, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 numbers, but since we start at 0, we only go up to index 9 in the values that we get. You know, we could basically similarly just find, individual values in here if we wanted to, just by saying like, what's random value at index 9? And it's 0.087, just like we saw before. So there's a few different notations you can use here to kind of extract out different slices from your data. But this is a useful one, and you can see, for instance, here that when we printed out random values, the first 3 values are the same as the first 3 values we have here. So we know that we did get the first 10 when we used this slice. So we did this stuff and covered it a little bit also with the Python lists earlier in the course. So we don't need to talk about this array slicing too much here. But one thing that's very common to do with NumPy arrays is to pick out some section of them where we want to find some additional information. And we could have a little bit of fun here, actually. So let's say we've got our first 10 values. Okay, well, hold on a second. First off, let's just take a look at some things we know that we can do with a NumPy array. One of them is that NumPy arrays have built-in functions, so these they're called methods, for doing common calculations, like calculating the minimum, the max, and the mean values of random values, or of whatever your NumPy array is called. Now we should expect with 100,000 values that we should get pretty close to minus 0.5 and pretty close to 0.5 with random numbers when we have 100,000 of them. So we could say, like, what's the minimum value in random values by doing random values.min, and that gives us a number that is pretty close to minus 0.5. And likewise, we could take copy and paste down here the same thing where we say random values.max, and sure enough, we get something that's very close to the positive 0.5 that we would expect. We could also take random values.mean, which should give us the average value. And in this case, our average, we should expect, with our random distribution of numbers, the average should be around 0. And oops, I have to spell it properly for that to work. But if we do random values.mean, sure enough, we get a number that's quite close to 0 for the average value. So that's nice. And that kind of makes sense because when we just have equally distributed numbers between 0 or minus 0.5 and 0.5, right in the middle of that range is 0, and we should expect our mean value to be close to that. What's cool with these NumPy arrays is we can also then take them and do these calculations on slices of the data. So like, let's say we just want to take the first 10 values and calculate what the minimum is of the first 10 values. We can do that basically by still using this dot min, but putting in here the square brackets and the colon 10 to say we should take values 0 to 10, values with index 0 to 10, and calculate what their minimum value is. And when we do that, we see we get a quite different minimum than we had before, because in the first 10 values, as you can see here, the smallest number is this minus 0.327, blah, blah, blah. And of course, as we expand that, that range, then we should expect to see getting closer to minus 0.5. Same thing goes if we do NP, or sorry, the dot max method here, then we see if we get 0.46. So we're fortunate in this case that we have one random number that's a bit bigger. And we could expand this a little bit. We could say like, what's the biggest random number in the first 100? And we see it's 0.48, and we could add more. First 1,000, and we see it's 0.49, blah, blah, blah. So it's nice that you can do this, these kind of common calculations on the whole NumPy array or any little piece of it that you can slice out. So with the interest of time in mind, because unfortunately I have to run to another meeting here shortly, I'll show one last thing, and then if there are remaining questions, then I'll have to come back to those the next time. But what I want to show here is another example where, let's say we want to find all the positive values we have and find the mean value of all of the positive numbers in our random values array. First step is to figure out how do we get all the positive numbers from random values. So one is we could make a mask, and a mask is basically just an array of true or false values that correspond to some test. This will make sense maybe when I explain it. So if we said that random values that are greater than 0.0, and if I just run this, what's going to come back is an array of true and false values. So anytime that random value is not meeting this condition, I get false, and anytime it's greater than 0, I get true. If we go up here and look at the first 10 values, sure enough, this first value is negative, so that test is false. The next value is positive, that test is true. So with that, then we could say we have this thing that we could call a mask. So random mask equals, and I'll just copy and paste this test that we have here. And so this is going to be an array of true or false values. So then what I can do is take our random values array, and from that random values array, I can select only the values where I have met this condition of being true or being positive numbers. And I can do that by saying, instead of a list of index values in here, I can list this true or false array. So we have random mask. What this is going to do is return a slice out of my array where the values that are going to be returned are those that meet this condition that was used to make this random mask. So in this case, it's going to be only the positive numbers from the array. If I run this statement, now what you see are only positive values. And if you're looking, for instance, to trim out data based on the date or based on certain temperature conditions or whatever the case may be, this is one approach you can take, which is to basically create the masks and then take out values using those masks. Now, in this case, we've made this random mask and then used that variable to slice things out. We could also just say random values, and then in the square brackets, say that we only want the random values that meet our condition of being greater than 0. So hold on just one second.
Hi.
Hey.
How are you?
Good. I'm in the middle of an online meeting, but we'll be, do you know where the room is?
Yes.
Yeah.
4:13.
It's just past the coffee.
Okay.
I'll be there in just
Okay.
5 minutes.
Okay. See you.
Nice to see you. Okay, sorry about that. So yeah, we can basically put this condition inside the square brackets and just as easily return our values the same way that we did by creating the mask here. The reason that you might want to create the mask separately, as I think is mentioned in the video for some of the lectures and also maybe mentioned in the hints, is if you have multiple arrays where you want to cut out values from the same places. So like, let's say we had a random values array and then we had a random temperatures, and we only wanted the random temperatures when the random values were positive, for example. Then we'd want to make this mask, or we would possibly want to make the mask to cut those data out. There's other cases where you could also maybe eliminate some values, and you want to make sure that if you're removing values from your array, for instance, like if you've got numbers that are listed in the array as not a number, NaN, you may want to drop those, and in those cases, often what you want to do is make a mask separately and then drop all of the values or all of the rows where you have an NaN from all the arrays after that. So yeah, that's most of what I had to say. I think the essence is here. I'll add one thing, and that is that just like we saw with the index slicing, that you can calculate these common calculations for some NumPy array, you can also do things like calculate what the mean value is of a slice using one of these masks. So random values with this condition that random values are greater than 0. So this is only going to give us the numbers that are meeting this condition. And then we'll calculate the mean of those. Sure enough, we can do that, and we get something that's close to 0.25, which is what we would likely expect. So I kind of rushed through some of this NumPy stuff a little bit, but unfortunately, I'm kind of out of time, and that's going to have to be where we leave it for today. I guess next time we can come back and maybe talk a little bit about pandas and NumPy in more detail if needed. I'll try to get the link for the next web stream up maybe a bit earlier so people can add questions and comments there as well in advance, so that we can deal with that stuff. And I could be ready to kind of know what things you would like me to discuss in more detail. But yeah, unless there are any urgent questions, I think I'm going to have to stop here, and I'll wait just a moment. I don't know what the lag is, but there's one general question. Yeah. Are both of these NumPy and pandas used commonly in work life? Yeah, so that's a good question. And I would say if you're a Python programmer, if you're a data scientist, or if you're, a kind of increasingly, if you're just a professional geoscientist and you've got some idea of how to use Python, I would say both NumPy and pandas can be commonly used. It depends a little bit on the flavor. If you're a geophysicist, you're probably using NumPy a bit more. If you're dealing with large data files, you might be using pandas more. But they're both very widely used libraries and very actively used and being kind of continually developed. And I would say, for a simple answer, yes. They're not obscure libraries that nobody knows about or nobody uses. You start Googling around for questions about NumPy and pandas, and you'll find hundreds of answers for all different kinds of things. So the good news is that, yes, they're common enough that you can certainly rely on Google and Stack Overflow and things like this for helping you solve some of your challenges with pandas and NumPy. So good question. Anything else? I'll wait just a second because I know I'm a little ahead. But if not, I'd say we'll plan to continue next week. I don't think I've got any kind of conflicts on my calendar, so I'll plan to set up the stream and do the same thing like we just did. Again, remind you to post questions in advance if you want, or if you've got friends in the course or other instructors who have questions that you know about, you can also post those, and of course, since it's recorded, they can watch then whenever it's convenient for them. So, yeah, I think that's it for today, and we'll continue next week.